So to finish things up, we want to kind of ask the question, given that in order for a multivariable limit to exist, its value has to be the same no matter how we approach that point that we're trying to approach. It's a valid question to wonder, like, what is the standard? What's the burden of proof? What do I have to do in order to show that a multivariable limit does exist? How many different approaches do I need to check before I can be sure that the limit exists? If all of the approaches that I check agree, is that going to be enough? And so in our previous activity, we had this example of a multivariable function where every straight line approach to 0, 0 ended up giving us a range of different limit values. And so we could say, well, any straight line approach is going to show me that this limit does not exist. And so a valid question might be, well, if I check every single line that approaches the origin through any different slope, and if all of those line approaches to the origin have the same value, then can I say good? Does this limit definitely exist? And this last activity for the day actually gets us to investigate that question. So this is activity number 3 in this section. And I'd like for us to do this just graphically, but again, it would be good for you and your team to work on the algebraic investigation of this outside of class. So here is our function, x squared y over x to the 4th plus y squared. And they are sort of leading us through the question, what happens if we approach the origin along a straight line, so a straight line with an arbitrary slope, and then see if the behavior that's being predicted by those straight lines is enough for us to guarantee that this limit exists. So in this GeoGebra worksheet, what we have is a straight line making an angle of theta. And so you can use this theta slider to investigate all of those different examples. And then for the last part of this activity, they're having you look at a approach to the origin along a parabola. And so this little slider here lets you look at different parabolic approaches, so along a quadratic curve toward the origin. So I want to give you just a few minutes to just sort of play with this and record take some screenshots and record your responses within your worksheet. So as we approach the origin with this function along straight lines, what we're seeing here are curves that look like they sort of stay attached to the origin in the XYZ plane as we move around on this, right? And so what I kind of see in this picture is as we approach the origin along any one of these lines, we're going to end up with the z value going to 0, right? Because we're always sort of attached there to the origin, even though some of these approaches, so if I just pause this for a second, some of these approaches look like as we're getting close to the origin, they sort of ramp way up, but then they eventually just come right back down to 0. So as you approach the origin along those linear paths, it looks like you're always going towards 0 in the z value. So then the next step, maybe return your first slider to 0, just so that it sort of sits on the x-axis. And now you have a quadratic slider, that's the second one down on this, to take some different quadratic approaches to the origin. See what those are doing. Here's the surprise about this function, right? That every single line that we approach the origin on is telling us that the z value is approaching 0, right? So the limit along any straight line path to the origin is the z value of 0. But if I take, instead of a straight line path, if I take a parabolic path, a parabola coming into the origin, so a path that approaches in this sort of fashion, right? Then what z value are we approaching along that path? It doesn't look like we're approaching the z value of 0.
Oh, I see. Oh, I see what you're saying now. Oh, I see
The
what
height of that parabola is not going down to 0 as we come in towards the origin. So all of these straight lines approach 0. But if I approach along this parabola, it looks like 1/2, maybe? If you look at the coordinates on that axis, let me spotlight my video one more time, right? So actually, this is kind of a good perspective to see. So this moving line here, that's all of my linear approaches toward the origin. And then right here on the tabletop of this mesa here, that's my parabolic approach to 0 that comes in at a height of not 0, but of 1/2. And this slider, you can choose other parabolas other than the one that was asked for in the problem. And it turns out that we get other heights. But it's just the one at the coefficient of 1. So this is the y equals x squared parabola. Gives you a height of 1/2. I think it's the highest value that you can get as you approach the origin. So what are you tempted to conclude for this function about whether the limit of this function as we approach 0, 0 exists? So this limit does not exist, even though every single straight line is telling us the same story. If we take something that's not a straight line, like you take this parabola, it's giving us a different answer.
Yeah.
So what the troubling thing about this, right, is that the question, what is the standard of proof to show that a limit does exist, it's not even enough to check that every straight line approach to the point gives us the same answer, because there might still be a curvy approach that gives us a different answer, as there is in this example. So it's a lot easier when we reduce the multivariable question to a single variable question. That's a good way to show that a limit does not exist. But it usually is not enough for us to show that a limit does exist. So for the most part, whenever we argue that a limit does exist or that a function is continuous, we're going to fall back on sort of some basic properties of continuity. Things like every polynomial function is a continuous function. Every exponential function. All of the functions that we learned about in single variable calculus were continuous. Those functions as multivariable functions will also be continuous. So something like, x times e to the y, that's going to be a continuous multivariable function because f of x equals x was continuous in single variable calculus. F of y equals e to the y was continuous in single variable calculus. And when I multiply two continuous multivariable functions, I get a continuous multivariable function. So that's kind of the good news, is that all the nice functions from calculus that were continuous, if I fiddle around with them and put some new variables in them and a variety of different variables, and I smush them together with arithmetic and composition of functions and all that stuff, that those compositions and sums and products and quotients are all still continuous as multivariable functions because they were continuous as single variable functions. So that's the good news, is that it's not going to be enough for us to check enough approaches to guarantee that a limit exists. But if we can justify that a function is continuous using single variable calculus principles, then those combinations of those single variable functions, when they make multivariable functions, they make continuous multivariable functions. So even our example from this activity, right, x squared y over x to the fourth plus y squared, this had a problem at the origin. And it had a problem at the origin because even though it is a quotient of the continuous function x squared y divided by the continuous function x to the fourth plus y squared, that quotient of continuous functions is not guaranteed to be continuous when the denominator is 0. Right? It's only guaranteed to be continuous when the denominator is non-zero. And sure enough, here it is. Every other point on this graph, other than the point at the origin, we do have a continuous function, right? An unbroken surface. It's just that at the origin, we have trouble, right? Because that denominator is becoming 0. So we study the pathological cases to trouble the concept just a little bit. But then after we move on, for the most part, all of the functions that we need to be continuous and well-behaved in multivariable calculus will be, because their single variable analogs were nicely behaved and continuous when you studied them in single variable calculus.